In the previous video, we studied the sum and product rules and factorials. Today, we will solve combinatorics problems on these topics. If you wish to review the theory, you can click on the link in the corner now, and come back. Let me briefly remind you of the theory. We use the sum rule when we choose either an object A in M ways, or an object B in M ways. We cannot choose A and B at the same time. They are multiply exclusive. The total numbers of choices is n plus m. We use the product rule when we choose A and B simultaneously. The total number of ways is n times m. And the factorial of a natural number n is the product of all integers from 1 to n. It's written as n and exclamation mark. Let's solve some tasks. Problem 1. Which 5-digit numbers are more numerous? Those that are not divisible by 5, or those in which neither the first nor the second digit from the left is a 5? Solution. A 5-digit number can be written as A, B, C, D, E, where A is a digit from 1 to 9. It can't be 0, otherwise the number would not be 5-digit. And the other digits are from 0 to 9. Every fifth number is divisible by 5. The smallest 5-digit number is 10,000. The largest is 99,999. Hence there are 90,000 5-digit numbers in total. By the sum rule, each number either is or is not divisible by 5. Since every fifth number is divisible by 5, that is 90,000 divided by 5 is equal to 18,000. The 90,000 minus 18,000 is equal 72,000 5-digit numbers that are not divisible by 5. Now consider 5-digit numbers with the restriction that the first two digits are not 5. By the product rule, we multiply the number of choices for each digit. For digit A, we cannot use 0 and 5, so there are 8 possibilities. For digit B, we cannot use 5, so there are 9 possibilities. For digits C, D, E, there are 10 possibilities each. The total is 8 times 9 times 10 times 10 times 10, that is 72,000. Thus both sets contain the same number of numbers. Its answer. Remark. We could also obtain the total number of 5-digit numbers by the product rule. 9 times 10 times 10 times 10 times 10, that is 90,000. For numbers not divisible by 5, note that a number is divisible by 5 exactly when its last digit is 0 or 5. Hence, to avoid divisibility by 5, we have 8 choices for the last digit, giving 9 times 10 times 10 times 10 times 8, that is 72,000. Problem 2. How many natural divisors does 720 have? Solution. Factor 720 in 2 primes. 720 is equal to 2 to the power of 4 times 3 to the power of 2 times 5 to the power of 1. Our divisor is of the form 2 to the power of A times 3 to the power of B times 5 to the power of C, with A from 0 to 4, 5 choices, B from 0 to 2, 3 choices, and C from 0 to 1, 2 choices. By the product rule, the total number of divisors is 5 times 3 times 2, that is 30. Problem 3. How many 3-digit numbers contain exactly 1 digit 7? Solution. Write a 3-digit number as A, B, C. We must place the digit 7 in exactly one of the 3 positions. If 7 is the first position, A is equal to 7, then B and C can be any digit except 7. Hence we get 1 times 9 times 9, that is 81 numbers. If 7 is in the second position, B is equal to 7, then A is not equal to 0, and A is not equal to 7, and C is not equal to 7. So we get 8 times 1 times 9, that is 72 numbers. Finally, if 7 is in the third position, C is equal to 7, then A is not equal to 0, A is not equal to 7, and B is not equal to 7. So we get 8 times 9 times 1, that is 72 possible numbers. By the sum rule, the total is 81 plus 72 plus 72, that is 225. That's answer. Problem 4. A phone pin consists of 4 digits. John calls a pin lucky if the sum of the outer digits equals to the sum of the inner digits, e.g. 1324, because 1 plus 4 is equal to 3 plus 2. He uses only lucky pins. If John forgets one digit but remembers its position, he can recover the pin. If he forgets 2 digits but remembers their positions, he only has to try a small number of possibilities. Item A. How many pins will John have to try in the worst case? Item B. How many lucky pins are there in total? Solution. Item A. Suppose 2 digits are forgotten. 2 cases are possible. The forgotten digits belong to the same pair, both outer or both inner, or they belong to the different pairs. If they belong to the same pair, the sum S of the other pair is known. The forgotten pair must consist of 2 not necessarily distinct digits where the sum equals S. The sum S can be from the 0 to 18. If S equal to 0, then exists only one pair of digits to get it. 0 is equal 0 plus 0. If S equal to 18, then exists only one pair of digits to get it. 18 is equal to 9 plus 9. If S equal to 1, we get 2 different pairs of digits, 1, 0 and 0, 1. If S is equal to 17, we get pairs 9, 8 and 8, 9. We can see that for a given S, the number of ordered pairs xy of digits with x plus y is equal to S is S plus 1 when S from 0 to 9 and 19 minus S when S from 10 to 18. The maximum occurs at S is equal to 9, given 10 possibilities. If John forgot digits from different pairs, then now he will have to try the possible sums. From the remaining digits, he can understand that the sum of S is not less the sum number. The maximum of the remaining digits. We will designate it max. And then he must go through all possible sums. The sum, however, cannot exceed 9 plus min, which means that he will have to go through 9 plus min minus max plus 1 values. In the worst case, when min is equal to max, this is 10 options. So the answer to point A is 10 options. Item B. Now count all lucky pins. Let the common sum be S from 0 to 18. As argued above, the number of ordered pairs of digits with sum S is S plus 1 when S from 0 to 9 and 19 minus S when S from 10 to 18. A lucky pin consists of 2 such pairs, one for the outer digits, one for the inner digits. Using the product rule, for a fixed S there are n of S squared lucky pins. Summing over all S. Adding the squares. 2 times 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49 plus 64 plus 81 plus 100. That is 2 times 285 plus 100. That is 670. Therefore, there are 670 lucky pins. Now let's solve a few other problems that involve enumeration and also belong to combinatorics, though they don't directly use the sum or product rules. Problem 5. On a small island, 2/3 of all men are married, and 3/5 of all women are married. The total population is 1900. How many humans are married? Solution. Let A be the number of men, B the number of women. Since every married man has a married woman and vice versa, the number of married men equals the number of married women. Denote this common number by x. Then we get x divided by A is equal to 2 divided by 3. X divided by B is equal to 3 divided by 5. Hence, A is equal to 3x divided by 2, B is equal to 5x divided by 3. The total population is A plus B is equal to 3x divided by 2 plus 5x divided by 3, that is 19x divided by 6, that is 1900. So x is equal to 600. Therefore, there are 600 married men and 600 married women. That is 1200 married people in total. Problem 6. Which rectangles with integer sides are more numerous? Those with perimeter 1996 or those with perimeter 1998? Rectangles A times B and B times A are considered identical. Solution. For a rectangle with sides A, B, the perimeter is P is equal to 2A plus 2B. Let D is equal to P divided by 2 be a semi-perimeter. Then A plus B is equal to D, with A from 1 to B. The number of distinct rectangles equals the number of integers A from 1 to D divided by 2. For P is equal to 1996, we have D is equal to 998. The number of rectangles is 998 divided by 2, that is 499. For P is equal 1998, we have D is equal to 999. The number of rectangles is 999 divided by 2, that is 499. Thus, the two sets contain the same number of rectangles. It's the answer. Recall the menu problem from the theoretical video. A menu has 3 sections: 5 salads, 3 soups, and 4 main courses. How many ways to choose a lunch if we may skip any dish? Here we add a skip option to each section. Hence, the number of choices is 5 plus 1 multiply 3 plus 1 multiply 4 plus 1, that is 6 times 4 times 5, that is 120. How many ways to choose a lunch if you may skip exactly one dish? We can skip exactly one of 3 sections, or skip none. If we skip salad, we get 1 times 3 times 4, that is 12 choices. If we skip soup, we get 5 times 1 times 4, that is 20 choices. If we skip main course, we get 5 times 3 times 1, that is 15 choices. Finally, if we skip nothing, we get 5 times 3 times 4, that is 60 choices. Using the sum rule, we must add all these numbers. We get 12 plus 20 plus 15 plus 60, that is 107 ways. That's answer. How many ways to choose a lunch consisting of exactly 2 dishes? This is the same as the previous count, but without the skip nothing case. Hence the answer is 12 plus 20 plus 15. That's 47 ways. How many ways to choose a lunch and optionally 1 extra dish from any section? The extra dish may be of the same type as already chosen. Firstly, choose a basic lunch, no extra, 60 ways. If an extra salad is added, we get 60 times 5, that is 300 possibilities. If an extra soup is added, we get 60 times 3, that is 180 possibilities. If an extra main course is added, we get 30 times 4, that is 240 possibilities. Total: 60 plus 300 plus 180 plus 240, that is 780 ways. That's the answer. Today we practiced combinatorics problems using the sum and product rules. Subscribe to the channel and like the video if you enjoyed it. Your support helps create new content. You can also support me with a donation by the Patreon or the donation alerts. The links are in the description. Until next time, Math is life.